What?
The function changes.
The function changes from.
Negative, positive.
I asked for relative max, right? Can you draw a relative max for me? That's the problem. Relative max. What's the function doing?
Oh, increasing.
Changes from increasing to decreasing. That's a relative max. Absolute max is the highest point. Daisy, is it possible for a relative max to be the absolute max? Does it have to be the absolute max? Absolutely not, right? Okay, new question for you all. All functions have an absolute max and an absolute min. All functions have an absolute max and an absolute min. How many guys would say true? How many guys would say false? Okay, Abraham, why false?
Because it depends on, like, if the function reaches infinity on one of the endpoints.
Yeah. If the function is heading up towards infinity, is there an absolute max? No, because the absolute maximum has to be a point. We're good? All right, so there was something that we studied last week. It was called, there was a name for it, there's a poster right behind me, not you. Okay.
The right endpoint.
It's the extreme value theorem. The extreme value theorem says that all functions have an absolute max and an absolute min. True or false? False. All functions have an absolute max and an absolute min. False. The extreme value theorem, there's two conditions that you're looking for. What's one of them?
It must be continuous.
Okay, I don't know what it is, but I think you mean the function must be continuous, and Jasmine, the other condition is?
It must be on, the function must be on closed interval.
If the function is continuous on a closed interval, you have a definite start and a definite end, then what do we know for sure, Noemi?
That it's what's the name? And continuous?
If the function is continuous on a closed interval, then the thing that you know for sure is...
Oh, it has absolute extreme.
It has an absolute max and an absolute min, an absolute highest point and an absolute lowest point. Either inside the interval, right, or the other place?
Outside.
Or inside or outside. I mean, I kind of see, I set you up for that failure there. Okay, either it's inside or it's the endpoints. We don't look outside if we're on a closed interval. We're okay? All right, good. So I want to do more application problems, but I want to give one more tool in your toolbox. Okay, up until right now, if I said show that a function has a relative maximum at x equals c, we have two ways. We've already heard those ways. Jose, what's one way?
If the function is changing from increasing to decreasing.
The function changes from increasing to decreasing at x equals c. That's a way, but I think somebody in the room knows another way. There's another way to show relative max. There's another way to show relative max. Just run beer? Oh, this is the way that everybody needs to know. The function changes increasing to decreasing, or it's something about the derivative. Something about the derivative. David, what about the derivative?
The derivative changes from positive to negative.
F prime makes a change from positive to negative at x equals c. Is everybody okay with both of these options? These are the two. Here comes the third way. I don't normally teach it this early in the course, but we're going to go this way. It's called the second derivative test. Anything with a name in calculus is always important. Here's how the second derivative test works. It says let f be a function such that f prime of c is equal to 0. This is the thing that has to be true. F prime of c is equal to 0. Can you guys show me what that might look like? F prime of c is equal to 0. What does that even mean? F prime of c is equal to 0. The derivative is equal to 0. What does that mean? What does that look like? I'm seeing some of this. This worries me. Because the derivative here is undefined, because it's a cusp point. F prime of c is equal to 0. What could that look like? What could that look like? Jose?
I thought like the absolute or whatever.
No, that absolute value graph has a cusp point. F prime of c is equal to 0 is what we call the horizontal tangent line. Horizontal tangent line. There are some different things the graph could do that would give you a horizontal tangent line. Jonathan, what's one thing the graph could look like and have a horizontal tangent? Okay, so it sounds like you wanted to do something like this. And that's x equals c. Is everybody okay? That's an example. Eunice, what else could happen?
Netflix have a minimum.
Okay, you could have a minimum like this. Okay, you might want to get these drawn on there. That's two ways you could have a horizontal tangent line. There's three more. One we haven't talked about in a very long time. I see the concave down kind. I see the concave up kind. There's some other kinds. We haven't talked about this in a while. Martier, do you remember? A what? A paddle point? Like I should come over and spank you? A saddle point. Like something like that guy there. That has a horizontal tangent line. So does this one, not cattle point. I think I kind of see where cattle point came from. Those are 4 examples of horizontal tangent line. The last one, I think it's kind of like the stupid example, but you never know. Would just be a horizontal line. Horizontal tangent line, right? These are 5 different ways you could have a horizontal tangent line. Let's look at the second derivative test. The second derivative test says if f is a function and the derivative is equal to 0, then look what happens. If f double prime of c is greater than 0, what would that look like? F double prime of c is greater than 0. This is telling you guys about concavity. F double prime of c is greater than 0. Can you guys show me f double prime of c greater than 0? What would that look like? F double prime of c is greater than 0. Means concave up. It's a cup that holds water. Okay, this is concave up. The second derivative test says f prime of c is equal to 0 and my graph is concave up. Look at those options over there. Horizontal tangent line and concave up. There's only one example that fits that. Which one? That's this guy over here, right? If you have a horizontal tangent line and you know the graph is concave up, your conclusion, what do you have to have? Not just a root. Look at that graph. A horizontal tangent line and concave up. We have a special name for this. It's a relative minimum. This is a new way to prove relative minimum without the number line test. For my friends that don't like the number line test, this is another option. All you need to know is that you have a horizontal tangent line and your graph is concave up. So talk to your neighbor about this next one. What's the conclusion? Yeah. F double prime of c is positive.
So we would have to take the derivative of this.
If f double prime of c is positive, that means f prime is increasing and f is concave up. It's this combination of horizontal tangent line and concavity together that tells you what's going on. All right, f double prime of c is less than 0, so my concavity must be concave down. I have a horizontal tangent line and my graph is concave down. Jasmine, what do you know for sure?
F of x has a relative maximum.
Relative maximum. I hope this just kind of makes sense. This might not be anything that you would ever write yourself, but it's another way to prove relative extrema. First, show me horizontal tangent line, then check the concavity to decide relative max or relative min. Here's the thing I want to make sure is really clear. If your second derivative is 0, the test fails. That doesn't mean point of inflection. I didn't say that. What it means is test fails. Sometimes they say inconclusive, meaning you can't use the second derivative test. You have to go back to the only other thing that you know that would work, which is the number line test. So this is a new tool in the toolbox. Okay? All right, let's talk to somebody there. You summarize the second derivative test. What do you know? How to use it?
There's a horizontal tangent line. The second derivative is that means that it's concave up and then If it's 0, then it doesn't work. Just concave out.
Yes.
If it equals 0, then it equals 0.
So what it means is, if you don't like using the number line test, you have another option. But if this fails, then you have to go back to the number line test. Okay? All right, so without looking, don't look, don't look, don't look, don't look, don't look. Don't look, don't look, don't look. Okay, just listen to the words that are coming out of my mouth. I've got a point, and the derivative is equal to 0, and the graph is concave down. What do you know for sure? Let's get some hands on this. Derivative is equal to 0, and the graph is concave down. Picture it in your head. Derivative is equal to 0, horizontal tangent line, and your graph is concave down. I'm going to wait till there's 8 hands up in the air. What do you know? I see 1, I see 2, I see 3, I see 4, I see 5. Anthony, what do you know? Horizontal tangent line and the graph is concave down. This has to be a relative max. Nice. Okay, horizontal tangent line and the second derivative is positive. Horizontal tangent line and the second derivative is positive. Noemi, what do you know?
So relative min.
Relative min. Second derivative positive means concave up, right? Horizontal tangent line and second derivative is equal to 0. Uh-oh. I think I've got like 3 people thinking about this. Horizontal tangent line and the second derivative is equal to 0. Jose, what do you know?
Another method.
You have to go with another method. The test fails. Inconclusive. We're good? All right, so let's do some optimization, shall we? It would be really good if you have a person that you're sitting next to, everybody's got a partner, that you're going to work with. We've got about 30 minutes. My goal is to get us through 2, maybe 3 optimization problems. You've got 5 minutes with this first one. Go as far as you can with the time that you've got. We'll talk in a little bit.
Is the 24th range is a principal line that's it, right?
Yeah, that's square root.
The margins at the top margins what should be the dimensions of the
So the area is
so like we're trying to find maximum. We're trying to use less paper so like we're trying to fit more.
yeah. This is x equals 0. X equals 2. This is what you add it up, you get 6. 4 equals 24.
Oh, you did?
Is that camera on?
Is it on? Yeah, it's on. like, it's only like the margins are.
It's 2.24 square inches. That means that is 8 frames. Because I have more than that. That means that y for the
Optimization or constraint? Constraint. So 24 equal to 2 is the constraint.
objective is equal to so 2x plus 2y. 2x plus 2y plus 4 plus 6. No, the objective is the perimeter. So what should the dimensions be of the perimeter? So the dimensions should be it's asking for the perimeter. It's asking for what dimension should be. So that's y plus x plus 2 y is objective 5. Right, that's the objective. We're trying to figure out what the y is.
Perfect time. All right, so let's get some hands on this. Using the variables that they gave you in this problem, what's the constraint? What's the constraint? You guys have had 5 minutes to play around with this. Anthony, what's the constraint? What has to be true?
24 equals x times y.
X times y has to be equal to 24. I agree with you. Where did it come from?
This side. 24 is the area.
24 is the area for the printing, right? And they've labeled it for you and said x and y, and this guy over here has to be 24. So you have a constraint that x times y has to be 24. Is everybody okay with the constraint? What's the objective function? What are you trying to make as big or as small as possible? Because this is where I've seen a lot of folks making mistakes. What are we trying to maximize or minimize? Hold on. What are we trying to maximize or minimize? Yes, the dimensions, but the dimensions that do what? Look at this problem again. The dimensions that do what? Because I see a lot of perimeter stuff happening here. This is not asking about perimeter. They want you to be able to do this with the least amount of paper. They're asking you about this. All the paper. What they're asking you for the objective is another area computation. But this time, it's a matter of this guy here comes that guy there. Well, how long is the paper going to be? The part for the print is y, but how long is the whole paper going to be?
Y plus 2.
It has to be y plus 2, because I've got an inch on this side and I've got an inch on this side. And I've got to think about how long that paper is or how tall the paper is. This part here in the middle is x, but I've got an inch and a half on this side and an inch and a half on this side. So x plus 3. The amount of paper, I could call it P or A if you want to, is going to be found by doing x plus 3 times y plus 2. That's the objective function. The hardest part in almost all of these problems is going to be that initial identification of the constraint and the objective, because I bet most of you, now that you've got the constraint and the objective, know exactly what to do. How many of you guys are feeling pretty good about moving forward from here? Okay. Go for another couple minutes, see what you can do.
So what's the plan here?
Okay, you want to find the derivative of the objective function. I agree, but there's a problem with that. So you can take the constraint.
We were adding the whole
Moving on, you go to the constraint, now it's setting go to the, this doesn't help you why.
There's some really good coaching happening here.
24 over y, and then there's just one, no, you go to constraint time.
Martier and Jasmine, are we okay back here?
How did I get to you? We have the constraint and we have the objective. The objective is the area. And so you go to the constraint divided by y or x and plug it into the area. You know what it is, right?
Alright, so from what I saw, just about everybody has rewritten the constraint as y equals 24 over x. Anybody go for x equals 24 over y?
Yeah.
Same thing. Ultimately the same thing. Right, but once you do that, Jose, what's your next move?
To find the derivative.
Whoa, wait.
What? No, I plugged that into the.
You're good, right? You're going to take this and you're going to rewrite your objective function in terms of that one variable. So x plus 3 times 24 over x plus 2. If I'm scoring this, that's probably going to get you the first point. You set this up. It's in one variable. Christian, what's your next move?
Now you have to solve for the derivative.
You're going to find the derivative, and then David, after that, what are you going to do?
Set it equal to 0.
Set the derivative equal to 0, and we're going to figure out what the derivative is undefined. So, options for finding a derivative here. Let's get some hands. What could you do? What could you do? What could you do? What could you do? Adriana, what could you do?
You could use the product rule.
You could use the product rule. That would work. There's another option here. Jonathan, what's your other option?
Can't you distribute first?
Okay. Would it be legal to distribute?
Yes. No. It's okay.
Yes, no, it's okay. So it sounds like you ended on yes.
Yes.
Right. By doing the algebra first, sometimes it makes your life a little bit better. So let's check it out. I would imagine a lot of you guys are going to go over here and do the box. X plus 3, 24 over x plus 2, 24 over x times x is, what is that?
24.
24. 24 over x times 3, 72 over x, 2 times x, 2x, 2 times 3 is 6. So my area is 24 plus 72 over x plus 2x plus 6, or even better, 30 plus 72 over x plus 2x. That's good. I think finding the derivative here is so much easier. So now you're going to go find the derivative, a prime. Derivative of 30. 0 derivative of 72 over x.
Negative 72.
Depends on how you think about this. Where are my quotient rule people? Anybody see this as quotient rule? Okay, maybe you see quotient rule. Maybe you see this as, let me do some algebra and make this 72 times x to the negative 1 power, then do a product rule, a power rule. Or you know what the derivative of 1 over x is. Negative 1 over x squared. So the derivative of 72 times that must be negative 72 over x squared. Lots of options. I don't care how you get there. Plus the derivative of 2x. That's got to be worth at least another point. The reason that you did that, though, and I'm going to go a little bit faster now, you want to know where's a prime equal to 0, so set negative 72 over x squared plus 2 equal to 0. Going to solve that for x. I think I've got some fraction killers in the room. So now I've got negative 72 plus 2x squared is equal to 0. So 2x squared equals 72, and x squared equals, what's it, 36. If x squared is equal to 36, then it should be x equals 6 and negative 6. Martyr's looking really good and powerful and confident with this. Okay? So we're done? We found the candidates? Right, then you've got to ask yourself the question, where is a prime undefined? Where is A prime undefined? Going to be at x equals 0. Okay. Great. I mean, this is the stuff that we've done three days going now. So you have candidates. You have candidates at 0, you have candidates at 6, you have candidates at -6. All three are candidates? Have a quick strategy conversation with somebody near you. How many candidates are there really? And why? How many candidates?
So there's plus and minus 4, but you can have negative for areas. So you can't have negative.
If you say more than 3, I'm going to die a little bit inside. All right, show me on your fingers, please. How many candidates do we actually have here? I see 2, 2, 2, 2, 2, 2. It looks like everybody's on 2. Jennifer, which 2?
The positive numbers.
Okay, so you're not going to go at -6 because?
You can have a negative.
Wouldn't make any sense to have a negative possibility, right? Could x be equal to 6? Yes. Could x be equal to 0? Look at what x represents in this problem. Could x be equal to 0? Oh, so sad. Oh, so sad. Daisy, what do you think? Can x be equal to 0 here?
I would say no.
Because?
Because they already give you the 1-inch margin.
Okay. But what does x represent? Look at the diagram. This is what we're missing. What does the x represent? X isn't the area. Look at the diagram. What does x represent?
The text.
X represents how long the text is going to be to get an area of 24. If you let this be 0, what are you going to multiply by to get to 24? It's not possible. Okay, Ramir, you've got some deep thoughts going on there. Be careful. Okay, so x equals 6 is a candidate. Now, here's where I think sometimes they're still getting into some problems. What are your endpoints? Okay. What are the endpoints for x? The question you want to ask, what's the smallest the x value could be? What's the smallest this x value can be? Look at your constraint. I need x times y to give me 24. What's the smallest x can be?
4.
I'm hearing 4. I saw 1. I'm hearing 1. The people that are thinking 1 are forgetting that could this side be even smaller than 1, like a half? Could I get an area of 24 if the height here is like half or 0.1 or 0.01?
So greater than 0.
Right, so the endpoints are x has to be greater than 0. And what's the biggest x can be?
23.9.
Okay, 23.99, that's because I think we're forgetting that 48 times a half is 24.
So,
Right? 48 inches tall and a ½ inch wide would give you 24 square inches of print. 96 inches tall times a ¼ of an inch wide gives you 24 square inches of print. So what's the upper limit? There is no upper limit, which is the problem. Since there's no upper limit, what this means is you can't do it the easy way. By the easy way, I mean you plug in the candidate, you plug in the endpoints, and you're done. So you can't do that. So your options, you get 2 options now. Option number 1 is the number line test. And I am pretty sure I've got some folks in the room that don't like doing the number line test. So option number 2 is the second derivative test. Okay. Well, I try to get it a little bit cooler. Go back to the second derivative test. Make sure you understand what the second derivative test says.
So if it's greater than 0, it can mean less than 0, max.
so the second you go, you put some relationship.
So the second derivative test says if your first derivative is equal to 0 and the second derivative is positive, first derivative 0, second derivative positive, what do you know about that, Jasmine? No, hold on, Jasmine. First derivative is 0, second derivative is positive, what do you know? Second derivative is positive, what do you know?
Concave, the function is concave.
The function is concave up, but if you also have a horizontal tangent line, Jasmine, stay with me, horizontal tangent line and concave up, what do you know? Concave up, that's why I want you to go back to the second derivative test.
There is a relative minimum.
You would have a relative minimum. Jasmine, what was the question you meant to ask me?
How did you conclude that there is no upper limit?
Wait, one more time.
How did you conclude that there is no upper limit?
There's no upper limit because I could go like 96 inches tall and 1/4 of an inch wide and still get an area of 24. Okay, let that sit for a little bit. So I want to use the second derivative test. The second derivative test only works if you first know the derivative is equal to 0. Do we know where the derivative is equal to 0?
Yep.
Where?
6.
6. And it's the only candidate. So go find the second derivative. Go find the sign of the second derivative and be ready to give me a conclusion. We know. At x equals 6, a prime is equal to 0. The only question is, what's a double prime? Lots of ways you can find the derivative. Quotient rule, you can do a little power rule action. Either way you do this, you should get 144 over x cubed.
You would do it for y world?
It's going to be same thing. Oh, wait. What did you get for a prime?
30 plus 3 plus negative 3 over y.
Then I think your next derivative is going to be 96 over y cubed. Okay, a double prime should be 144 over x cubed, whether you did quotient rule, whether you did power rule, whatever. The thing that I care about though is this. What's the sign? What's the sign of the second derivative at 6? Right, I don't want to hear anybody saying, oh wait, 6 cubed, that's 6 times 6 is 36 times 6, oh I was never good at that. All I care about is what's 6 cubed? Positive. So this guy here is positive. Your conclusion, at x equals 6, a prime is equal to 0, and second derivative is positive. Conclusion? Think about it if you have to. Horizontal tangent line and second derivative positive. So Martyr, what do you know? What you have is a relative minimum. So at x equals 6, a has a relative minimum. And I'm emphasizing that for a reason. Because we have a problem. We just did all this beautiful work, and you have told me that you have a what? A relative minimum. Knowing me, what's the problem here?
We need to find the absolute.
You need that absolute minimum. If you had endpoints, all you would do, Anthony, you'd plug 6 into the original function. You'd plug the endpoints into the original function and you'd be done. Here's the good news. You have one candidate. One candidate, and that candidate is the minimum. If you only have one candidate and that one candidate is a minimum, what do you really know? This must be an absolute, if this is the only thing the graph is allowed to do is decrease then increase, then it's an absolute minimum. So the last part is this. Since This is the only, emphasize only, relative extrema. Notice I'm not writing relative minimum, it's the only relative extrema. Then at x equals 6, A has an absolute minimum. And that's the conclusion. That's the thing that we really care about. Jonathan.
Didn't you say that there's no upper limit?
You're right. There's no upper limit.
So the limit is going to infinity?
You're right. So there's no upper limit. But I want the lowest point. I can have a lowest point even if there's no highest point. Here's what I want you guys to do. I think there's a lot of folks who just have some processing questions. There's 3 options on the next page. Strongly recommend try option 1. If you've got questions, let me know. We'll talk it out.
I got all the way to the 8.6 equals positive numbers, so I can tell that that's really high.
Because we're using the second derivative test, which is that new kid on the block from like 40 minutes ago.
So we already know that it has horizontal tangent.
Because that's how we found x equals 6, by setting the derivative equal to 0.
But it is a double prime.
You found the second derivative so that you could know the sign, which tells you concave up or concave down. And it's putting those together that tells you relative min and relative max. The graph will continue to increase after x equals 6. So if you only have that one candidate, if all that you have is that relative minimum, then that means the graph is just going to continue increasing. I know you're going to stop. So there's a couple of thoughts here. The extreme value theorem says if you have a continuous function on a closed interval, then what? Then you have to have an absolute maximum. You have to have an absolute minimum. That's what the extreme value theorem says. Okay with that thought? That doesn't mean I can't have them on an open interval. It says that if I have continuous on a closed interval, then I must have a max and I must have an absolute min. But since I'm missing the condition of continuity and I don't have endpoints, I don't have to have an absolute max and an absolute min. Good. Want to see that constraint in that objective function? The constraint is what restricts your choices. No, the objective is what you're trying to make really, really big or really, really small. Yes, cheaper. So the a squared plus b squared equals 25 to 5.
What is that equal?
That's what restricts your choices. What are you trying to make either really big or really small?
I'm afraid that you're not right one now. I know it says it. Wonder if BH.
So we figured out the constraint.
5.
The hypotenuse is 5
X squared plus y squared equals 5 squared.
squared.
That's
The Pythagorean theorem gives you your constraint.
yeah, that.
That restricts your choices. Or a squared plus b squared equals 5 squared. That's fine. But that's the constraint. I bet for both of you, once you identify the constraint and the objective function, you get it from there. But this is usually the requirement. Okay, so if we figured out the constraint, what's the constraint?
C, right? Equals over here.
Which one is the constraint? The constraint is the one that restricts your choices. That's the one that usually involves setting your equation. I can't pick any x and any y. I have to pick them so that x squared plus y squared equals 5 squared. That's why it's a constraint. Right. The fact that you label them badly is not the end of it. But just so that when we're having conversation, we can have good conversation. I want to make sure that we know which one's the constraint. So that's your objective function. What are you going to do? So you solve the constraint for y, you're going to plug it in over here, and then your next move is right. After you, like, even with the DC, it was that initial setup that was. Once they got here, they're like, oh, I know what to do. I'm going to comment directly. Do you have endpoints on this one? So is there a smallest x and is there a biggest x? You've got your triangle. What's the smallest x you make?
So negative 1.
Above 0.
Okay, and what's the biggest x?
What did you say about that?
If the hypotenuse is 5, the hypotenuse is always the biggest side. So x cannot be bigger than 5. So this is not going to be one of those problems that goes on forever. You do have endpoints, so you don't have to do second derivative tests. You don't have to do the number line test. But you still could if you want to. Okay, where are we?
We just found it objective.
What is the objective? Oh, x times y over 2. Okay, good. So, good. And really, x squared plus y squared equals 25? Neither one is easier than the other. Okay. All right, so sadly, that was the bell. For those of you looking for more practice with objective function and constraints, for these 3 problems, the objective function and the constraint are at the bottom of the paper. I'm also going to send you guys the solutions. This is not homework. I want to make sure we are using as much time in class to work on these because these are some butt-whooping kinds of questions. Okay? I understand that. So tonight's homework is the multiple choice corrections to the trimester exam. You've got the document you picked up on the way in for each of the 30 multiple choice questions. It tells you what the answer is. You have to indicate, did you get it right or did you get it wrong? There's a little hint on the far right, so you're going to go through, you're going to work through as many of the mistakes as you can, and you're going to summarize your results. The whole thing is due Wednesday. I'm giving you guys 2 nights, because some people are missing like 15 or 16 of these questions. It's going to take you some time. I'm here after school today till 5:30, tomorrow until 5:30. We can turn that off. Thank you.